Okay, hi, good morning. So today we're going to carry on our discussion about bias-variance trade-off. So it's on the second part. And we're going to conclude this section today. Starting from next session, we're going to have a couple of sessions about validations and different methods involved with validation. Then starting from next week, we conclude the course with SVMs. Yeah, we're probably gonna have 4 or 5 sessions in SVMs, and then you'll have your final exam early April. All right, so if you recall, previous week we talked about the other method we can use in order to define the complexity of your hypothesis. So we started from using Hefting's inequality, and then we define VC dimension. Now we are talking about bias-variance trade-off. And we said, for instance, in your training set, if you have a training set of D that contains number of point x1 and y1 in a case of a classification, and they are coming from a distribution of P of D, so we can call it P of D. The output hypothesis that we selected was G of D, right? It's a function that tries to mimic your unknown F. And your Y hat would be the estimated value of the Y with that G as your candidate hypothesis. So we have a function which is unknown, which is F. We had a set of hypotheses. We have a training set. We have a data set of D, and we selected G of D, a function to mimic F. That was the estimated value with that function. So if you pass X points here through this function of G of D, it's going to give us some estimate of the point, and then we have to compute this with respect to the real value of Y and come up with some metrics in order to compute the error, compute the other metrics that we discussed this semester. All right. So we also define G bar here as the average of hypotheses, and we would define it with expected value of D of GDX. So suppose you have many hypotheses, which obviously in many cases you have in your set of H, and depending on the data, you pick one of those G's, so you're going to have multiple G's. We can get an average over those using their expected value, and we call it average hypothesis G bar, right? So now, suppose you have multiple data points now. So instead of 1D, you have D1, D2, up to dk. And these are k-independent samples drawn from PD, right? Thus, if you take k-independent samples from D, D1 up to dk, so we're going to have, again, G1D, G2D. All of them are drawn from their respective, D, up to GD of K, right? So these are going to be the associated output hypothesis. In this case, we can define G bar, or the average hypothesis, by the division of the summation of all those G's by the number of K that we have them. So K, if it's K is 10, we're going to divide it by 10. And this K can go up to infinity, right? Because we can draw many times the samples, K-independent samples from our, D. And this happens many times because depending on the hypothesis, we might take different samples, or depending on taking different samples, we might come up with different hypotheses, right? So now let's see how we're going to use bias and variance metrics in order to observe the complexity of a model. If you recall previous session, we talked about two simple examples. So I'm just going to recap them here. So suppose your hypothesis was a constant one. Say in a linear case, you have, so it's just a line, right? So it's a line. Suppose this is your axis. So this is your H1, for instance. And your function was sine pi of x. Your x's were between -1 and +1 window. And you have 2 points named as u and v, right? So your you are coming from a uniform distribution between this window, and v would be the output of your function sine pi v, right? So now if we take 1 point only, that's why n is 1. It means that we just, in this case, we have two hypotheses, green and blue, and these are 1 point that they hit to the real function, which was unknown. So we're going to have gd1 of x, and we have gd2 of x, right? So just like what I mentioned in the previous slide, we're going to define g bar as the expected value of d gd of x, which is equal to ev equal to 0. And then we talked about how we're going to compute bias and variance. So bias was the difference between your g bars and the real function f of x raised to 2, and the variance was the expected value, the expected d of g dx minus g bar x, right? All right, so let me just have the graph here. Okay, I mean, in practice, we mostly only have one realization of the d, right? We might not have multiple d's like d1 up to dk. So we can compute g bar, but in general, we use g bar as a useful conceptual quantity, right? In most of the cases, when we deal with test cases, like we have 1D, so g bar would be the same as your g, but in general, there is this useful conceptual quantity if you wanted to generalize to more, more sort of a general form as a conceptual form. All right. So also we define average test error delta x, which was the difference between your expected E of D of, so this is the G and the F squared. In this case, for the case of your sine pi of x, your bias would be 0 minus sine pi x squared, because the first value was 0. That was your G. Thus, in this case, it would be equal to this, x1. Now let's talk about the variance. So our variance in this case would be the expected value of v minus 0 here raised to 2. Thus it's going to be E of v2, because this would be 0 only. You're going to have only v2. And v2 would be the expected value of our function raised to 2, so it's the square of that, which is going to be sine 2 pi u, right? And this would be equal to the area that our function represents in a graph, right? In the case of square, so suppose you have another function like this, so you have to compute them as well. So this would be area from the window of the points which we have the uniform distributions. So plus the window would be from -1 to 1, P of u sine 2 pi u du. So so in this case, if you want to compute the variance, you have to compute this integral. This would be equal to 1/2 of this, because this one came out, the integral, and the final result would be 1/2. So your variance would be O.5 in the case that you have a constant hypothesis and a sine of p of x function, right? Now that we computed the variance and bias, we can go on and compute the delta x, right? Average test error. Which was the v minus sine pi x raised to 2 and this would be equal to, so you expand this v2, this function raised to 2, and also we have minus here, so it's going to be -2, the first value and the second value, so v and sine. This would be equal to the expected value of the first one raised to 2, the sign, and minus 2 of both two values. We knew that this one was 0, so the expected value of v was 0. So the whole thing on this side becomes 0. And the final result for your delta x would be half plus sine 2 pi x. So your bias would be half, your variance also is half, and E out, the out of sample is going to be 1, right? So now let's see what we can learn from these numbers. What do we learn if a bias is higher or a variance is higher or lower? How are we going to describe the complexity of a model with such metrics, right? So just before that, let me just let me recap on another notation that you might see in the notes or in your assignments, and which is LHS, or Latin Hypercube sampling. It's a form of random sampling with some small tweaks. So instead of a complete random sampling, LHS, what it does is it decides how many sample points to use, first of all. Say we're going to use 4. And for each of the sample points, it remembers both the row and column in case of 2D, say it was a 2D case, in which the sample was taken. So if we use the first row, the second sample wouldn't be using the first row anymore. Or if we would have using the second column, on next generation we don't use that second column anymore. We want to make it as random as possible. So this form of random sampling is called LHS, Latin Hypercube sampling. If you want to visualize it as an example, so assume you have n rocks, right, on a chessboard, and you want to distribute those n rocks in a chessboard in a case that they don't threaten each other at all. So you want to distribute them in a way that their row and columns are completely distributed with no threading. So in 2D, say you have 4 points. I've shown them in black, blue, green, and red, right? If you want to have LHS form of a random sampling, this could become this. So you make sure each row and each column are having one sample. So this is a form in statistics. Normally they use LHS, and this one of the cases of using this is for Monte Carlo simulation. So just to let you know, in Monte Carlo simulation they are trying to explore many different variants of your hyperparameters in order to come up with a solution. So one of the ways to explore that is using an LHS. You want to make sure you're exploring evenly all of your optimization space. All right. So if you recall in the previous slide, what we gained as our delta x here was actually the value of bias and variance. You see our delta x? So this is going to be interesting because using bias and variance, we can compute now the average test error. So this is another method we can use to come up with the description of, quality of the model. So let's have a proof on that. All right. So we're trying to provide a proof with delta x equal to bias plus variance. So say if your samples are coming from LHS, so you're going to have the expected value of gdx minus g bar x and plus g bar x minus fx all raised to 2. So in order to expand it raised to 2, we name the first two components A, the last two components B. So you're going to have a squared b squared plus 2ab, right? Thus we're going to have ed equal to gdx minus g bar x raised to 2 as our value A. Then we're going to have b value square, g bar x minus fx square as our b value, b square, and then plus 2 a and b. So a value was g bar x minus fx, b value was gdx minus g bar x. All right, so we carry on. This become ed gdx minus g bar x, right? Plus this value raised to 2. And then this coming out, 2gx minus fx multiplied by expected value d gdx minus g bar x now. So we knew that this one was 0. We computed it before. So this 0 was all this multiplication. Thus the final value is again the same as your value of variance and bias, right? So this shows that your delta x average test error is equal to your variance and bias. Okay, so now using these two metrics, we can define trade-offs, right? what if one goes up, the other goes down? And what if a model has a higher bias versus the other? So how do we describe these two? You recall we would define bias as how well can your hypothesis approximate the function y, and variance was how well does the output of your candidate hypothesis change with d, right? So these were the definition of these two. So let's talk about an example where your hypothesis is small, right? So you have some points shown here by crosses. You have a small hypothesis that obviously cannot approximate well your f of x. So suppose your f of x was here. You have this amount of differences, right, between your hypothesis and the real function y, right? So the differences here is called bias in this case. Suppose you were using this point as your this hypothesis as your candidate one, so g bar of x, g bar function actually, and since you had only one hypothesis, so g bar would be equal to your g, right? So we have a small hypothesis. This one is small. The difference is huge between your estimated value and the real function. So you have this amount of distance. So we call it bias. So the bias is large. On the other side, it doesn't change that much when you change your data point, right? So interestingly, when you have a small hypothesis, your variance would be small as well. So now let's talk about the other extreme point. You have a very large hypothesis, or maybe multiple hypotheses, as this G, as a set of H, right? You might have multiple candidates, right? You might have multiple hypotheses here, and this one was your candidate, this function G bar, and that was your real value, that was your real function that you would like to estimate, and now you see that you're pretty closer to your unknown function because you have a larger hypothesis. It covers, the chances are higher that it covers more points, and it's it generalizes better with your unknown output. So your bias would be smaller, obviously. However, the whole circular here, the whole thing would be your variance. If you change your degree, it's going to change. So interestingly, when you have a large hypothesis, your bias would be equivalent to a smaller case, but your variance becomes larger. And this is the major difference between having a large and a small hypothesis. So, in the case of a small, both your G and G bar are the same, right? Thus your variance is very small. In this case, your G is very likely to be close to F because you have a larger area here, But on the other side, your variance would be large. And it's the size of this region, right? Okay, is that clear? All right. So, let's talk about the test error, out of sample error for your G of D. Just like the previous case, we need to compute the area that this function shows, gdx minus f of x. So the differences between your estimation and the real function over your data set, px dx, right? However, we know that E out of gd is a random quantity. It depends on the way we sample it randomly, right? It's a test case. So, in order to compute that, we would need to consider expected D of E out of GD as the test error itself. So this one becomes a test example for itself because it's a random quantity. So in this case, we would define out of sample error as the expected value of the out of sample error of the G, right? And this would be equal to the area of the PD E out GD D of, this is your data set. So instead of your smaller x's, now you're going to have it over all the D, right? All right. If we expand this, we're going to have integral of PD, and this would become this. E out of GD would be another integral. We described it here. So it's going to be gdx minus fx. The difference is raised to 2 px dx. And you try to solve this. It's going to be the first integral of px over the inner one. This one itself has PD gdx minus fx raised to 2 dx. So you got the point here? Because the E out itself is random, in order to compute the test error, we have to treat it as another test example for itself. That's why we are making it a nested function here. All right, continuing with this, we're going to have the integral of px expected the ed of gd minus fx, and then this will bring us again our delta x. So your test error would be equal to the expected value of the average error, which is sort of intuitive for us. We knew that delta x would be bias and variance plus of these two. So the E of x of delta x becomes E of x bias and variance. You make it disjoint, and then it would become bias bar and variance bar in your test examples. So this is another generalization for computing your test error using these two metrics, right? We're going to compute the bias bar, which is all of our biases, and we plus them with the variances, all the variances as a variance bar. All right, as another example, you remember in the previous session we had two different hypotheses. This one was a constant one, a simpler one, and this was a linear case, right? Say a little bit more complex to some extent. So you see that the bias is higher, however the variance is smaller. It doesn't change that much with changing of the b. On the other case, this linear G, the bias is smaller, right? However, the variance is much higher. At some point it's closer, like at some point it's like hitting it here, here, here. At some point it's far away, right? Also here. So the variance is larger. You see the difference here now? Okay, so using this we can define what we call learning curves. So we already talked about it in VC dimension. So assume your y-axis pertains to expected error on both cases, and your x is number of samples, so number of your data points defined by n. In a very simple model, so you're going to start with a higher out of sample error, and the more you go with the number of samples, the more you train your model, this will decrease a little bit, but it stays somewhere here, right? So the performance of your model is not that good. However, it converges faster, you see? So starting from like almost this point, you didn't improve that much up to a very, high number of n. On a very complex model, your final expected value becomes smaller, so your performance would be better of the model. The quality is better. However, your test error starts way, way higher. By the time your n goes to a very large number, it goes down, right? And at the end, you're going to stay in a better point than a simple model. Okay, so if you're gonna summarize in a table, I mean, you already knew that. So a simple and complex model, your bias for the simple model is gonna be higher, obviously. Your convergence would be faster, it's gonna converge faster, you saw that in the previous case. You need lower number of samples. Your final error would be high. And in a complex model, it's going to be exactly the other way around. So your bias would be lower. Convergence is going to get slower. So when you have a more complex model, it takes more time, more iterations in order to converge. But if it converges, the final error is going to be lower. So this is another interpretation of the previous graph. All right, and then next one in my final slide, I sort of brought up the comparison between using bias-variance trade-off versus using VC dimension that you saw in previous lectures. So we can use both cases in order to, define complexity for our learning curve, right? So this is the table of comparison. The first one is VC dimension. The second one is bias-variance trade-off. So the error metric that VC dimension uses is classification error, right? We saw that. Whereas the error metric that bias-variance uses is basically a square error. You just define your estimate function, you compute it, and a distance between the estimated function and the real function raised to 2, right? The complexity measure that VC dimension uses is exactly the VC dimension of hypothesis. The complexity measure that bias-variance use is variance. Learning algorithm for VC dimension is going to be independent. However, in the case of bias and bias-variance trade-off, the learning algorithm affects choice of your candidate function. So these are the major differences. And coming here, so this is how VC dimension defines your learning curve. So that was your, say, optimal VC dimension, right? In sample error and out of sample error. And here in this case, we define it using variance and bias to define the delta x, right? Is that clear? Great. So you survive 95% of the course materials already. So we're going to have a couple of sessions about validation, which is going to be fun. And then we conclude with SVMs next week. Right. Have a good day, guys.